Good day to you all. I'm Sokumaran Gautaman, and today I'm going to present a systematic study of three-set solver algorithms. In this presentation, first we will see the introduction of what is a set problem, and later on we will move to basic definitions and terminologies associated with set problem, and afterwards we will delve into two well-known algorithms to solve this three-set problem, namely DPLL and CDCL, and afterwards we will discuss the experimental testing which we had done for these problems, and finally we will conclude. The Boolean satisfiability problem, often abbreviated as SAT, is the problem of deciding whether there is an interpretation that satisfies a given Boolean formula. In other words, it tries to determine whether the variables in a given Boolean formula can be consistently replaced by the values of true or false, causing the formula to evaluate to true. As in the case of arbitrary formulas, determining the satisfiability of a formula in conjunctive normal form where each clause is restricted to a maximum of 3 literals is known as three-set problem. The first problem to be proved to be a NP-complete was SAT. Even though NP-complete problem has a worst-case scenario of exponential time, many of the real-world SAT problems can be solved much faster. Now let's see the basic definitions and terminologies of a three-set solver. Not all the variables of the formula are assigned at a given moment of time. Some are assigned and some are not assigned. Such a state is called partial model. Under partial model M, the literal P is true if MP evaluates to true and P is false if MP evaluates to false. Otherwise, P is unassigned. Under partial model M, a clause C is true if there is a literal P in C such that P is true, and a clause is false if for each literal P in C, literal P is false, otherwise C is unassigned. Under partial model M, the C-norm formula F is true if for each clause C in C-norm formula F, clause C is true, and C-norm formula F is false if there exists one clause C in C-norm formula F such that C is false, otherwise F is unassigned. C is a unit clause under M if a literal P in C is unassigned and the rest are false. Literal P is called unit literal. Firstly, we will look into DPLL algorithm. This algorithm is named after 4 computer scientists whose work had been extensively helpful in devising this algorithm by early 1960s. In DPLL, a partial model is maintained and it is built recursively. Initially, the partial model is a null set. In DPLL, variables are chosen randomly and assign values of true or false in a recursive manner, but sometimes due to unit literals, this assignment is forced. We will see the DPLL algorithm now. The input is C in a formula F and partial assignment M, and the output is whether the formula F is satisfiable or unsatisfiable. The first step is decision step. In DPLL algorithm, it randomly chooses a variable P and assign a random bit of true or false, and if the assignment results in a partial model where the formula is satisfiable, it will return SAT, else it will flip the assignment and recursively go ahead to the next random variable. In the base case, this formula F is true if all the clauses in the partial model M returns true. In that case, it returns SAT. At the same time, the formula F is false at least one of the clause in the partial model M is false. In that case, it returns unset and it backtracks to the last decision which was made, and from there it will make a new assignment to the last decision variable and it will build upon a new partial model from there onwards. Here, sometimes when a literal P is identified as a unit literal, it has to be assigned a value of true, and if a literal is negation, then it will be assigned a value of false, so negation of that literal will result in true. Based on DPLL algorithm, a DPLL run consists of 3 types of actions. First one being decision. The second is unit propagation. It relies upon the previous decision what we have made, and the third being backtracking. It occurs when a partial model encounters a conflict. Let's see an example. In this example, there are 8 clauses and some variables, namely from P1 to P7. First of all, I'm arbitrarily taking variable P6 and assigning true to it. This makes clause C8 a unit clause and literal negation of P5 a unit literal, because here, in order for clause C8 to be true, P5 has to be assigned a false value, and after assigning that, in the rest of the clause there are no any other changes. So I'm moving forward and arbitrarily taking another variable P7 and assigning false to it. That also doesn't make any other change in the rest of the clauses. So I'm arbitrarily taking another variable P1 and assigning true to it. This makes clause C5 true, and at the same time it makes clause C1 and clause C2 unit clauses, because in clause C2 already we have assigned P1 true, so negation of P1 is false, and P5 have been already assigned false, so P3 had to be true. So based on this assignment, clause 6 becomes true, and already based on the assignment of true to P1, clause 1 is a unit clause, so P2 had to be true based on clause 1. After this assignment, clause 7 becomes true, and based on this assignment, clause 3 becomes a unit clause, and here P4 had to be true based on clause 3. After this assignment, we can see a conflict in clause 4, because already we have assigned true to P3 and P4, and both are in the negation form, so C4 is false. Here we can see the variable P6, P7 and P1 are decision variable, because for them we have assigned the values, and for the rest of the variables, unit propagation decided what value they should contain. So in case of a conflict, DPLL backtracks to the last decision variable and flips the assignment. So here for this example, P1 will be assigned to false, and it will move forward until we find a satisfactory or unsatisfactory answer. Now we will see conflict-driven close learning algorithm, CDCL, which was proposed in late 90s. It is inspired from earlier DPLL algorithm and shares the same structure. Before delving into CDCL, we will see its specific definitions. Current partial model that has not reached to the conflict yet is called the run of a CDCL. While deciding and propagating, a data structure is constructed to observe the run and avoid unnecessary backtracking. It is called close learning. During a run, the number of decisions after which the literal was made true is its decision level. There is an implication graph in the form of DAG, where nodes are true literals and conflict nodes, and there will be an edge between two literals L1 and L2 if L2 is caused by unit propagation due to the decision made in L1. During a CDCL run, the above data structure is maintained and each node is annotated with decision level. Let's see the previous example using implication graph. P6 is the first randomly assigned variable, so it's in decision level 1. This makes clause C8 a unit clause, and as a result, negation of P5 is assigned 1 at decision level 1. Negation of P7 is randomly assigned as true at decision level 2, and P1 is assigned as true at decision level 3. Assigning of P1 and P5 triggers clause C2 as unit clause, and as a result, variable P3 is forced to be assigned as true at decision level 3. Assigning P1 as true triggers clause C1 a unit clause, and as a result, variable P2 is assigned as true at decision level 3. Assigning P2 forces clause C3 to be a unit clause, and as a result, P4 is a unit literal which is assigned as true at decision level 3. Assigning P4 and P3 creates a conflict in clause C4. In case of conflict, the CDCL algorithm traverses back the implication graph to find the set of decisions that cause the conflict. Here in this example, the negation of P6 literal at decision level 1 and the literal P1 at decision level 3 are the root cause which cause this conflict. This can be found through backtracking with the aid of these edges. At the same time, here we can see the literal of negation of P7 is not connected by an edge to the conflict node. That means this literal negation of P7 doesn't have any impact, or it is not the reason for this conflict. Here, the clause of the disjunctive negation of the causing decision is called the conflict clause. For this example, the conflict clause is P6 disjunction negation of P1. Afterwards, we will add the conflict clause in the input clauses of the CNF formula F, and it will be backtracked to the second last conflicting decision. Here in this example, the first last conflicting decision is at decision level 3, the second last is at decision level 1, and we will backtrack to this decision level 1, and from there onwards we will proceed like DPLL. Adding conflict clause does not change the set of satisfying assignments, and it implies that the conflicting partial assignments will never be tried again. By adding a conflict clause, it prunes away the search space. It records the past work of SAT solver, and at the same time it enables many other heuristics to be added on without much complications. Let's now see the CDCL algorithm. The input for this algorithm are CNF formula F, partial model M, and decision level DL. Firstly, the decision variables are assigned, and after each assignment, the DL variable is incremented by 1, and the corresponding unit propagation is carried out. When CDCL algorithm faces conflicts, it analyzes the conflict and it creates the conflict clause. Using the conflict clause, it correctly updates the DL current decision level, and it resets the D stack to the current decision level and creates a new partial model. This learned conflict clause is included in the CNF formula F. This process is repeated until F is unassigned under M or partial model M not equal to F. Here, the important difference between CDCL algorithm and DPLL algorithm is here only it returns unset if the decision level at 0, all the clauses in partial model returns false. Both DPLL and CDCL algorithms were implemented in C++ language in Linux environment, and they were tested against 8 different benchmark CNF formulas. Here the first CNF formula consists of 20 variables and 91 clauses, and the final upper bound CNF formula consists of 200 variables and 860 clauses. Each test case is run 10 times, and average time taken for all these 10 runs are being recorded. Here you can see the DPLL algorithm takes a time of 2.2 milliseconds for the first CNF formula to run, and it takes about nearly 5 minutes to run the upper bound CNF formula, whereas the CDCL algorithm takes about nearly 1 millisecond to run the lower bound CNF formula and takes about 3 minutes to run this last upper bound CNF formula. From the first scatter plot, we can see for large size input, CDCL algorithms performs better in case of time, and the same plot is again plotted in the base of log 10 for time taken, and when we scrutinize the time taken for very small size inputs, again it is proven that CDCL algorithms performs better in low size input also. So we can assert that for all the benchmark test cases, CDCL is efficient than DPLL in terms of running time. From the previous experimental study, it has been shown that CDCL algorithm performs better than DPLL algorithm in terms of time, and through this state space graph, it can be again shown that CDCL algorithm is efficient than DPLL algorithm in terms of memory. So it can be concluded that CDCL algorithm is more efficient than DPLL algorithm in terms of running time and memory usage. For practical real-life applications, CDCL algorithms can be used to solve 3-set problem. Thank you for listening to the presentation. Have a great day.